Imagine we have a particle next to a heat reservoir. Also assume that there are only two energy states available for the particle to occupy. If the particle chooses to reside in the ground state, its energy would be zero. The particle can also borrow some energy from the heat reservoir and upgrade its energy state to the higher level that is available to it. In statistical physics, the probability that a particle resides in a state that requires energy equal to, let's say, epsilon, is given by this equation. This probability function in classical physics is the Boltzmann distribution. In the case of quantum statistics, and depending on the nature of the particle, this is the Bose-Einstein distribution or the Fermi-Dirac distribution. In machine learning literature, this is called the softmax function. Here, T is the temperature of the reservoir, K is the Boltzmann constant, and Z is the partition function, a normalization factor that should be tuned such that the sum of all the possibilities is equal to 1. For our particular example of a single particle with two energy states, there are only two possibilities. In the first possibility, the particle is in a state that requires zero energy, and therefore the probability is 1 over z. The other possibility is that the particle resides in the state that requires energy equal to 1, and the probability is equal to the exponential of -1 divided by kt, the whole thing divided by the normalization factor z. To calculate the partition function explicitly, we know that the sum of these two probabilities must be 1. Therefore, the partition function is equal to this sum. And keep this equation in mind as we get back to it later in this video to construct the logistic regression model in machine learning. Let's now switch the gear and see how this physical system of a particle next to a heat reservoir with access to two energy states is equivalent to logistic regression in machine learning. Let's assume that we have collected some data and stored it in a spreadsheet. And the last column of the spreadsheet is a binary variable. Let me clarify what I mean with a few examples. Let's say I have measured the body fat and body muscle and height and weight of 1,000 people and store them as x1, x2, x3, and x4 columns of my spreadsheet. And as the last column, which I label y, I record the gender of the person, female or male. As another example, let's say I have measured the speed, acceleration, price, and weight of 1,000 cars that are either a Toyota or Mercedes. So my spreadsheet columns x1, x2, etc. are the speed, acceleration, and other features of the cars, and the last column that I label y is the make of the car, Toyota or Mercedes. Now I conventionally label one category in the y column with 0 and the other category with 1. For example, in the case of gender, I can label female with 1 and male with 0. Or in the case of cars, I can label Toyota with 0 and Mercedes with 1. The same goes for any other spreadsheet with a categorical binary variable. So regardless of the system or experiment, the last column of my spreadsheet has values of 0 or 1. This column is equivalent to the energy state of the physics example earlier in the video. One state, for example, if y is equal to Toyota, has the energy of 0, and therefore we report y to be 0. And when y is equal to Mercedes, the energy is 1, and we set y to 1. In summary, the last column in my spreadsheet is the energy state of the spreadsheet and can take two categories or energies, 0 or 1. The rest of the columns in my spreadsheet act like the heat reservoir in the physics example. I can multiply each of them by a constant beta to be estimated later and add a constant beta 0 to the sum and that would be equal to the -1 divided by the temperature T times the Boltzmann constant K. In other words, the x1, x2, x3 columns tune the temperature of the spreadsheet. Let's now get back to our probability description of the physics system and see its different parts in terms of the spreadsheet we just discussed. If you have watched the other videos in this series, we always write probability in the following form and call F the effective free energy. In this case, the effective free energy is equal to the energy epsilon divided by the kT. As we discussed, in the case of a spreadsheet, the energy epsilon is just the y column with categorical values. So let's replace epsilon with y so that we are consistent with the conventions in machine learning. Also keep in mind that -1 over k times t is related to the rest of the columns in the spreadsheet by this equation. Just so you know, this form of distribution is also known as the Bernoulli distribution. To keep the notation simple, we always show the partition function as the sum over the exponential of minus effective free energy. In this particular case, since the system has only two energy states, the sum has only two terms. Before I move to the next subject, let me remind you that in this video, we started from the general form for probability, which we previously called the God equation, and wrote the effective free energy in terms of its Taylor series. We then ignored the higher order terms in the Taylor series using the maximum entropy principle to derive the linear regression in machine learning. The question is if we can perform the same here. And the answer is no. The reason is that the coefficients of the Taylor series are derivatives of f with respect to the column variables. And in this case, the derivatives with respect to the y column are not well defined since y is not a continuous variable. It's a categorical variable. Now let's switch the gear and extract the model of logistic regression from the probability distribution. That means we want to express the expected value of the variable y, the energy state, in terms of the rest of the columns. To calculate the mean of y, we have to get back to the partition function that we computed earlier and add an auxiliary variable j to its argument. We will set j equal to 0 after whatever calculation we do. Let's now take a derivative of both sides of the partition function with respect to j and then set j equal to 0. Now divide both sides by the partition function, and the left hand side is the definition of the mean of y. The right hand side relates the mean of y to the temperature of the spreadsheet, which is defined by this equation in terms of the rest of the columns of the spreadsheet. Now let's assume, as we will discuss it in the future, we have estimated the beta parameters using the spreadsheet data. We can then use this logistic regression model to predict the expected value of the y if we collect data about the x1, x2 and other columns of the spreadsheet. The error on our prediction is equal to the root square of the variance of y. By definition, the variance of y is equal to the expected value of y squared minus the expected value of y to power 2. To calculate that, let's take a second derivative of the two sides of the partition function with respect to the auxiliary variable j and then set the j equal to 0. Now divide the two sides by z. The left hand side is the definition of the expected value of y squared. Let's now put its equivalent on the right hand side into the equation for the error of the prediction. And here is our error estimation for the predictions we make using our logistic regression model. Let's now switch the gear and explore the properties of the probability of the two energy states of the y column. Also, we want to investigate the expected value of the y column as well as its error. We would like to see how the temperature of the reservoir, in other words, the rest of the columns of the spreadsheet, will affect these terms. Let's start with the probability of each of the two values of y, the energy states, in terms of the temperature of the spreadsheet, the heat reservoir. As you can see, at low temperatures, the probability of the state with zero energy is close to 1, and the probability of the state with energy equal to 1 is close to 0. The reason is that the temperature is an indicator of the amount of energy the heat reservoir, the x1, x2, and x columns of the spreadsheet passes into our particle, the y variable in the spreadsheet. When the temperature is low, little energy is passed to the y variable, and it does not receive enough energy to go to the state with higher energy to take the value of 1. So it has to stick to the value of 0. But when the temperature is high, the particle or the y column has enough energy to take any of the two energy states, and therefore the chance of taking them becomes equal, the 50%. Now let's change the x-axis and instead plot for minus of 1 over kt, which in terms of the spreadsheet variables is a bunch of beta constants multiplied by the x1, x2, and rest of the x variables. This time, we also allow negative temperatures. As you can see, the probability of the two states switches between 0 and 1. When the x-axis is far negative, y equals 0 is our prediction. And when the x-axis is far on the positive side, y equals 1 is our prediction. And here is the mean of the y, which is our prediction for it, and the root square of its variance as the error of the prediction. As you can see, the error on the prediction is very high at the center where the temperature is infinite. That is because, as we just saw, at very high temperatures, both of the values of the y column, both of the energy states are equally possible. And when the temperature goes close to 0, the far right and far left of the plot, the error goes to 0. One interesting point is that the left-hand side of this plot corresponds to negative temperature. If you wonder what negative temperature is, in physics, we can define negative temperature for systems whose maximum energy state is not infinite, like in this case that the upper energy state is just 1. In such systems, the negative temperature is just an indicator of how far away energy of the system is from the maximum energy state. As the last chapter of this video, let me say a few words about how we estimate the unknown beta parameters. I'm going to leave an in-depth explanation for another video. The conventional approach is to define a type of error function, a loss function, and minimize it. Depending on our interests, we can choose different error functions. Precision, accuracy, sensitivity, and many more are among the possible measures that we can use. As I explained in this video, a non-conventional physics-based approach, if we don't want to go the minimization route, would be to use the partition function and calculate the expected value of the x variables and their multiplications and form a system of as many equations as the number of unknown parameters. Then use the law of large numbers to find the empirical values of the expectation values from data and insert them into the system of equations. Finally, solve the system of equations to find the estimates for the unknown beta parameters. I hope you have enjoyed this video. Take care and see you in the next video.